Welcome everyone. For today's prep, I want to look at one more example for calculating our intervals of concavity. So we're going to look at this one example, and we know that if we want to find the intervals of concavity for a function, we need to let's kind of go through the steps again. So the first step is we need to calculate the second derivative and factor it. So when we're trying to find the intervals of concavity, we use our second derivative. And then once we have our second derivative, we want to look for the possible inflection numbers. So we want to get those inflection numbers. And there's two ways we can get this. Either the second derivative being equal to 0, or the second derivative not existing. And then once we have those inflection numbers, then we want to do our sign chart, and this is ultimately going to give us our intervals of concavity. So we do our sign chart for f double prime. All right, so this is our general strategy. In general, if we have a function f and we want to find its intervals of concavity, we need its second derivative. So for this example, we're actually given the second derivative, and it's already factored for us. So sometimes we have to calculate it and do all the factoring. We got to do the heavy lifting. Here, kind of nice, second derivative is given to us, and it's factored. So we have the second derivative is x plus 1 times x squared times 3x minus 9 raised to the power 5. All right, so the first step for this problem is actually done for us. Okay, so sometimes this part takes us some work. We gotta do some stuff. So now let's look at finding the inflection numbers. So these are going to be the places where our function might change concavity. All right, so second derivative being undefined. This usually happens when we have division. And there's no division here. We're not dividing by x. There's no negative exponents, so we're not kind of being sneaky about dividing by x. So in this case, none. We're not going to get any inflection numbers this way. So you want to look for division by 0 for those. Where we are going to get stuff, though, is from our second derivative being equal to 0. And when it's nice and factored like this, we've got three separate factors. We've got the x plus 1, we've got the x squared, and then we've got the 3x minus 9 raised to the power 5. So what we can do is we can set each of those factors equal to 0. And we're going to be able to solve each of these for x. All right, so let's start with that first one, the x plus 1. Subtract 1 from both sides. We get x equal to negative 1. For the next one, do the square root of both sides. We get x equal to 0. And when we do these, when we look at these power functions, we want to undo this exponent. So when we have the squared, we're really going to do the square root of both sides. So in the case where we have raised to the power 5, we're going to do the fifth root of both sides. And that's going to cancel off the exponent, and it's going to leave us with just the stuff inside, and then a root function applied to 0 is just going to be 0. So another way to kind of think of this, when we have a term that's being entirely raised to an exponent, really the only way that term can be 0 is if the stuff inside the power is what's equal to 0. So just like here, we had x squared equal to 0. That gave us, if we look at the stuff inside the squared function, it was just the x. So for this one, if we look at the stuff that's inside the raised to the power 5 function, that's going to be just the 3x minus 9. So we could set that just equal to 0 and then solve for x. And when we do it for this one, we get x equal to 3. All right, so in this case, we end up with 3 inflection numbers. So these, again, are the places where we might have an inflection point. So then we do our sign chart. We get our sign chart ready. So we draw our x-axis. And we're going to plot these 3 numbers that we just found. So we've got -1, we've got 0, and then we've got 3. And what these numbers do is they slice up our x-axis for us, and we end up with a few different intervals. And our goal is ultimately to figure out what the sign of f double prime is on each of these intervals. And that'll tell us if our function is, the original function is concave up or concave down. So to help us with this, we're going to write down a few extra rows. So we're going to have 3 extra rows here. We don't want to do too much in our head. It's easy to make little mistakes. So we're going to have 3 separate rows here. And what are the rows that we're going to use? Well, we're going to just use each of these factors. So let's label our 3 factors here. So we've got x plus 1, that'll be the top one, then x squared, and then 3x minus 9 raised to the power 5. Okay. So we're going to figure out the sign of each of these individual factors for the intervals, and then we'll put it together to get f prime, or f double prime. All right. So let's start with the easiest one. So we have an x squared here. So whenever we have an even exponent like this, an even exponent always gives us something positive. So we can go right across, and for each one of these intervals, x squared is going to be positive. All right, so we can deal with that. So then the other two, here we have just x plus 1. So that one we're going to have to use test numbers for. And then odd exponents also can be positive or negative. So it's only even exponents that are always positive. All right, so what are some test numbers? So the way we can think of this, we want to take some test numbers. So for the first interval, something less than -1. So -2 would be good. And we're going to plug it into the x plus 1 factor. And when we do that, we get -2 plus 1, which is -1. So the result is negative. And when we take -2, plug it into this factor here, we get -6 minus 9, which is -15. And -15 raised to an odd power is going to be -15, or it's going to be negative. So a negative number raised to an odd power stays negative. So what we have then is we have a negative number times a positive number times another negative number. So we have a double negative. So those cancel out. And that tells us then that f double prime must be positive on this first interval. And when f double prime is positive, that tells us our function f is concave up, the original function. All right, so then we just play the game and go to the next interval. So for the next interval, we're in between -1 and 0. And we could do another test number. Now, a way to kind of maybe do this a little quicker is for these odd powers, these odd terms like this, once we know how they start off, they're going to stay that way until we reach the x value that we got from its solution when we set the term equal to 0 and solve for x. So if we look at this x plus 1 term, it starts off negative, And it's going to stay negative until we get to the x equals -1. And once we reach that -1, it's going to switch signs. And then it's going to become positive, and then it's just going to stay positive. So we can kind of go through and fill in the rest of the row. All right, so same thing with this 3x minus 9 raised to the power 5. Once we know how it starts off, so in this case it starts off negative, once we know that it starts off negative, it's going to stay negative until we get to the x value we got from its solution. So it's going to stay negative all the way until x equals 3. So it's going to be negative on this interval, negative on this interval, and then once we reach x equals 3, that's where this individual term is going to switch signs, and it's going to become positive. Now, if you wanted to, you could check this out. So it's always a good way to check your work. Let's just check it for maybe this interval 0 to 3. Pick a test number is 1, and let's just double check. Let's plug it into both of those factors. So test number into the first factor there, we get 1 plus 1 is positive 2, positive. And then when we plug 1 into this factor, we get 3 minus 9, which is -6, and -6 raised to an odd power is still negative, so negative. So you could still keep using test numbers just to get the rest of them, but that's kind of like an easier, maybe a little shortcut. So for x plus 1, started off negative, and then at -1, where what we got from the solution, it switched signs and then just stayed positive forever. And then the 3x minus 9 started off negative. Once we got to the x equals 3, it switched signs and became positive forever. All right, so now we can just put it all together. For the next interval, we've got one single negative. So that means when we multiply a positive times a negative, the result is going to be negative. And when f double prime is negative, that means the original function is concave down. We go on to the next interval, see the same thing. We have a positive times a single negative. So that means our second derivative is negative, which means our original function is concave down. And then for the last interval, it's positive all the way down. So that means f double prime is positive, which means our original function is concave up. All right, so we've got our intervals here. And let me just check. Yeah, we just wanted the intervals of concavity for this one. So if we were double checking, we would need a little bit more information about this. But what we're noticing is that at -1, we're seeing a change in concavity. So we'd probably have an inflection point at -1. We would just need to know if it's in the domain of the original function. We're also seeing a change in concavity at x equals 3. So most likely 3 is also an inflection point. Yeah, we would just need a little bit more information. We'd need to know whether 3 is actually in the domain or not. And then same thing for, well, at x equals 0, we're not seeing a change in concavity. So we're definitely not having an inflection point there. But in any case, the question was just asking for the intervals of concavity. So we're ready to write those down. So f is concave up on the interval -infinity to -1 and on the interval 3 to infinity. And f is concave down on those two middle intervals, -1 to 0 and 0 to 3. All right, so I just wanted to practice this example, just because sometimes these types of problems where you're given a little bit more information, I kind of feel that these are a little tricky because we don't have to do all the steps. Some of the steps have been done for us, so just recognizing that is can be a little bit of a challenge. So for this one, we wanted to find the intervals of concavity for some original function f. In this case, we weren't given the formula for that original function f, but instead we were given the formula for its second derivative. So we're able to kind of like jump right in and start our analysis. All right, so we'll get a little more practice with these in class. So we'll see you then. Bye.